In this final video in the sequence of respiration, we're going to look at oxidative phosphorylation. In the previous videos in glycolysis and the citric acid cycle, we encountered two important high-energy molecules, NADH and FADH2. These high-energy molecules have to be oxidized using oxygen to realize the full energy potential of a molecule of glucose. Pictured here are the NADH and FADH2 molecules in their oxidized and reduced forms. NADH is produced at several stages. First at the glycolysis stage, where it has to be oxidized, otherwise pyruvate has to be converted to lactate. It's then produced just before the Krebs cycle when acetyl coenzyme A is formed, and then finally in the citric acid cycle. This is also when FADH2 is produced. Both of these have to be oxidized using oxygen, otherwise the citric acid cycle would stop due to a self-regulating feedback. Remember that oxidation is the loss of electrons. NADH and FADH2 lose their electrons, thus getting oxidized in an electron transport chain in the mitochondrial membrane. To really get the maximum out of a molecule of glucose, you need oxygen to oxidize the NADH and FADH2 molecules. So what is oxidative phosphorylation and how does energy get created? There are three steps to oxidative phosphorylation. First, electrons move from high energy states to low energy states, and in doing so release energy. That's the purpose of the electron transport chain. So over here, electrons flow, which are these purple circles, and as they move from the high energy state to a low energy state, energy is released. This energy then drives hydrogen ions from the matrix of mitochondria into the intermembrane space. That's the space between the inner and outer membranes to cause a proton motive force, or a PMF. So that's what happens when these hydrogen ions here in the matrix move into the intermembrane space, and then this potential energy of the PMF is harnessed using ATP synthase to produce ATP. ATP synthase is a specialized channel, and we'll look into that in more detail later in this video. So let's look at these steps in detail. Step 1 involves the electron transport chain. What is the electron transport chain? Well, it consists of many proteins grouped into three large complexes. NADH and FADH2 are electron carriers, so as the electrons from NADH and FADH2 are released, they pass through these electron carriers and hydrogen ions are transferred into the intermembrane space. There are two key players in the electron transport chain that you should be aware of, ubiquinone and cytochrome C. These help carry electrons from the NADH and FADH2 through the electron transport chain. This slide here shows the number of hydrogen ions that are transported at each turn. NADH transfers 10 protons. FADH2, on the other hand, only joins the process at this phase, at the cytochrome reductase phase, and therefore only transfers a total of 6 hydrogen ions, or protons. So step 1 was where we looked at the electron transport chain. Step 2 in the process of oxidative phosphorylation is the generation of a PMF, or proton motive force. This happens through the different conformation of those different complexes in the electron transport chain. And that's what this slide here shows. Essentially, as electrons from NADH and FADH2 move through the electron transport chain, it gives energy to these complexes and allows it to transfer hydrogen ions. So this slide here explains what PMF is, or the proton motive force. It's basically like a battery, so it has stored potential energy due to the concentration difference, and then also a voltage difference. The stored potential energy due to the concentration difference is given by the pH, and there's a tenfold difference in the concentration between the intermembrane space and the matrix. There's also a potential energy difference due to the segregation of charges. Let's take a look at this energy a bit more quantitatively. So PMF, or the proton motive force, is due to the electrical energy and chemical energy. The electrical energy is due to the transmembrane potential, and we'll call that psi. The chemical energy is due to a variation of the Nernst equation. If we plug in values for RT over F, which are just constants, we get the number 59. If we plug that into this following equation, the energy from the proton motive force, which again is the difference in the electrical energy and the chemical energy, is given by this equation, which is psi minus 59 times the change in pH across the intermembrane space and the matrix of the mitochondria. The transmembrane potential which is the electrical energy or the transmembrane potential, is given by 160 millivolts. This is calculated using the Nernst equation by taking into account different ions that we'll see in another video. Remember earlier we saw how the change in pH between the intermembrane space and the matrix of the mitochondria is about 1, and if we plug that into this equation to calculate the chemical energy, we find that the proton motive force generates a potential of about 220 millivolts. If you plug into the Gibbs free energy here below, we get the Gibbs free energy for one hydrogen ion to move from the intermembrane space back into the matrix is about 5 kilocalories per mole. And that's pretty amazing because that means that when ATP is generated, it's an energy molecule that can be used to provide the energy needed for so many processes within the body. Alright, so the first two steps of oxidative phosphorylation were the electron transport chain and then the generation of the PMF. The final step in the oxidative phosphorylation cascade is the production of ATP. As a result of the proton motive force, protons flow through a channel called ATP synthase. In this figure, that's this channel over here. In the process, 2.5 ATPs are produced per 10 protons. So the proton motive force provides the energy to synthesize ATP. The ATP synthase is made up of two units, an F1 unit and an F0 unit. The F1 unit faces the matrix side of the mitochondria, while the F0 unit faces the intermembrane space of the mitochondria. So these are the hydrogen ions in the intermembrane space. They travel through ATP synthase to produce ATP. 4 protons are used to produce 1 molecule of ATP. 3 protons are used to make the ATP molecule, while 1 proton is used to transfer it to the matrix side of the mitochondria. So here's how the F1 and F0 units play together. F1 is made up of 3 beta units. Those are these purple structures that you can see. And there's also 3 alpha units. The F1 subunit of ATP catalyzes the synthesis of ATP. It has 3 catalytic sites that are identical anatomically but function differently at any given time. There's the open site, the loose site, and the tight site. The binding of ADP, or adenosine diphosphate, to one site promotes the release of ATP from another site. So where does oxygen come into all of this? Well, oxygen is the final electron acceptor. So all the electrons that are released from NADH and FADH2 finally go to oxygen, and that eventually forms water. This oxygen is extremely important. It needs to accept the electrons that travel through the electron transport chain so that the proton motive force can be generated. Without oxygen to accept these electrons, the proton motive force cannot be generated, and the full potential of glucose cannot be recognized. So to recap, we saw 3 processes: glycolysis, Krebs cycle, and oxidative phosphorylation. And this slide shows how the different molecules are transported. For pyruvate and phosphate groups that are negatively charged molecules, rely on positively charged hydrogen ions to be transported, and the pH gradient that again depends on the hydrogen ion. To recap, let's look at the ATP count from all these processes. If you add up the ATP by assuming that 2 NADH produces 2.5 ATP, we find a total of about 30 ATP produced from the entire respiration cycle. The reason the NADH in glycolysis gives a lesser amount of ATP is because this has to be transported from the cytoplasm, these NADH molecules, from the cytoplasm to the matrix of the mitochondria, and depending on the efficiency of the cell, some NADH can be lost. In conclusion, we looked initially at glycolysis, and we focused on the anaerobic aspects of respiration. We then looked at the Krebs cycle that occurs in the mitochondria, where more NADH and FADH2 are produced. And then we looked at the electron transport chain and oxidative phosphorylation that is the key component of respiration to generate high amounts of ATP. I'm attaching 2 short YouTube videos for your reference.